Hello, guys. Good morning. Good morning, everyone. Am I audible? If I'm audible, please write yes on the chat box so that I can proceed. Good morning, Rekha Karge. Good morning, Garima. Good morning, Mahima. Good morning, Ankita. Good morning. Good morning, everyone. Yeah, okay. I'm audible now. So, first of all, how was your paper on 17th? Can I know? Was it hard? Was it easy? For those of you who found it easy, little bit easy, they can write E in the chat box. And those who found it a little bit harder or very hard, they can write H on the chat box so that I can see. Yes. Good morning, everyone. Ria Oja. Yeah, I'm also excited, Ria. Okay, Ankita writes it's hard. Okay, Swami, okay, it was easy for you. Nice. Rohan, it was hard. Okay. Selva Priya. So for most of you, it was a little bit harder paper, right? Okay, moderate. Mahima says that it was moderate. Hari Yadav, it was hard. Sudhir, it was easy, right? Rekha Karge, it was easy for you. Nice. Anyway, for most of the people, it would be the paper was hard, I guess. Like for 60% of the audience, it was hard. And for some of you, it was easy. And for some of you, it was moderate. But I can understand that. Now, here after that, there will be 2 more CSIR NET papers. So it is an advantage for you. So whatever mistakes that you did in this particular exam, the concepts that you were not able to clear, or you found the paper a little bit harder. So you have 2 more chances for that. In this very year, try to clear your CSIR NET exam. You have 2 chances, and it is a bonus point for all of you. So you're coming, like you have given your exam right now. Now don't give yourself a break. Whatever concepts that you were not able to complete or you were not able to understand, try to go through those things again. And we'll be conducting these concept review series for you. Here you can like build up your concept and clear all your concept, ask questions. And in this way, for the next upcoming exams, you'll be prepared beforehand. So this is my personal advice for you. Don't give yourself a break because 2 more exams are yet to come. And in this very year, if you clear your exam, it would be beneficial for you. Okay? So am I making sense to you? Like, do you agree with me? Type agree in the chat box. Then we'll be proceeding. Yeah, all of you agree. Right. Okay, this time computer interference was very slow in the exam. Okay, Amit Thakur. Okay, there will be certain issues were there regarding the computer, okay? Uh-huh. Absolutely agree, okay. Technical issues were there, right. Online was in Hindi. Other in Hindi means whole complete question was not in one complete language. Okay. That was also an issue for you people. Mixed languages. No problem. Like whatever mistakes or whatever issues that you had in this particular exam, you can cover up in your upcoming exams, right? So let us start with the session. So my name is Neelam Mehra. Let me introduce myself. I'm an expert in Biotechnica. So from starting today, in this very entire week, we'll be covering all the 13 units of CSIR NET syllabus. And in that, we'll be covering the important concepts related to each and every unit, right? The concepts from which questions are majorly being asked in exam. So from exam point of view, we'll be covering all the concepts, and there will be certain free sample papers also available for you all that you can download from the link given in the description below. For that, you have to sign up. A feedback form would be there. After that, only you can proceed and you can download your free sample papers, right? So at the end of the lecture, you can do it before, because right now, if you start doing it, you won't understand the concept that I will be discussing for you, right? So let's begin. So before going any further, let me tell you what would be the topic of discussion for today's session. So we'll be covering Unit 1, amino acids. Here, firstly, we'll be discussing about, wait a second. So here, firstly, we'll be discussing about, we'll be doing comparison between the PI and pKa values. Okay, what is the PI value? What do you understand by the pKa value? And how do we compare? And what are different rules for these values that we apply for amino acids? That we'll be covering. And we'll be doing it with help of certain revision tools. Like concept table would be there, concept wheel would be there. These revision tools are specially being designed for you all so that you can find it easy in terms of your revision, or in terms of keeping those concepts in your memory at the time of exam, right? Then we'll be discussing about the acidic and the basic nature of amino acids. So how amino acids, they behave acidically or basically in an aqueous solution on the basis of the ionization of the groups. There are basically two groups, amino group and the carboxyl group, when and where they get ionized, and what is the behavior that they show in an aqueous solution. All these things will be covered. Then would be the PI and the pKa values of amino acids. These values you need to remember by heart. There would be a chart that I'll be discussing, a table form, in which there will be written the PI and the pKa values of amino acids, right? And then we'll be coming to the charge on amino acids at different pH values. So at different pH values, there are different charges on amino acids. How these charges vary at different pH values, that we'll be discussing. Right? Is it blurred screen? Now also, the screen is visible? Yeah, change the video quality to 720. Okay. Then we'll be discussing about the titration, the characteristic titration curve for general amino acids. General amino acids are those amino acids which have only two groups that ionize in the aqueous solution. We are not talking about the R group here. We are talking the two groups, that is the carboxyl group and the amino group. So all those amino acids which lie in this category, which have only two pK values for two groups, carboxyl groups and amino groups, for them, what would be the titration, the characteristic titration curve, that we'll be discussing. After that, we'll be coming to the titration curve for the special group of amino acids. First is the acidic group. The glutamate and aspartate amino acids, they lie in the acidic group. Why acidic group? Because they have an extra carboxyl group present in their R group. R group it acts as an extra carboxyl group in them. So what is the characteristic titration curve for these acidic amino acids, that we'll be discussing. After that, we'll be discussing about the characteristic titration curve for lysine and arginine, which also fall into the special amino acid group, that is the basic amino acids. These are being considered. So lysine, as we know, it has an epsilon amino group present in its R group. So its R group is an epsilon amino group, and for arginine, it's in guanido group. Right? So for arginine, the R group is guanido group. Both of these groups, because of their ionization, the amino acid acts as basic. So for them, they have a whole different titration curve. So how that titration curve is being formed and what do we understand about these amino acids through the titration curve, that we'll be discussing. After that, we'll be discussing about the characteristic titration curve of histidine. Now, histidine also falls into the same category of lysine and arginine. It is also a basic amino acid, but the titration curve for histidine is completely different from as compared to lysine and arginine. How it is different, that we'll be discussing. And at last, there will be certain questions on the basis of the whole discussion that we did in this session. Those questions you need, like you have to solve, and I'll also help you in solving those questions, right? Are we good here till here? Okay, discuss also the polarity. Mehraj, fine. We'll be discussing everything, whatever topic comes in this, right? Okay. So, starting with the comparison between the PI and the PK value. Now, you would have heard this PI and PK in your entire amino acid chapter. Now, how do we compare both of these values? What do you understand the PI value and the PK value? We'll be understanding both of these concepts with the help of this revision tool. This is a Conceptica table that is specially being designed by Technica for you people so that you find it easy to compare certain difficult topics, and terms which are so like very confusing and all. So for that, it is being designed and you can keep like those concepts in your memory for a longer period of time. So with this concept table, this revision tool will be discussing and comparing both of these values. So coming to the PI value, what do you understand by the PI value? So PI value, also known as the isoelectric point. This is the pH at which the molecule has net neutral charge. Means the molecule, that is the amino acid, it would be present in its zwitterionic form and there will be no charge, or the charge would be neutral on the amino acids. Then coming, what is pKa? Now pKa, it generally tells or it measures the tendency of a particular group in an amino acid, whether it is carboxyl group or the amino group, its tendency to lose its proton. That's the major, that is something which we can derive, like what pKa actually tells. So coming to the definition, like bookish definition, what pKa is actually, it says that it is an association constant. So as we know that Ka value, this is basically the dissociation constant, right? So opposite of it is pKa, which we consider as the association constant, right? So it is basically the negative logarithm of ratio of dissociated acid and conjugated base over the concentration of associated chemical. Now, what does this whole sentence actually means? So as we know, let us take an acid here. Okay, this is a weak acid. Let us consider a weak acid. Now this weak acid, when in aqueous solution, it gets dissociated into its conjugated base. This is the conjugated base and the H plus ion, right? Now, according to the definition, what is the value of, like, how do we calculate Ka? Ka is basically the dissociation constant of the acid in an aqueous solution. So this dissociation constant would be basically equal to the concentration of the conjugated base, the concentration of the H plus ion divided by the concentration of the acid that we took. So this is the value of Ka. Now here it says that what is pKa? pKa is basically the negative logarithm of Ka, which means it would be the negative logarithm of the concentration of the conjugated base, H plus ion, and AH, that is the acid. So this is basically what the sentence actually means in mathematical term, right? Is it clear for all of you? Okay, I need to change the ink. Right. This is fine? White is fine? Is it visible now? Type yes if it's visible. Okay. So till here, have you understood the concept? What this sentence actually means? An association constant, it is the negative logarithm of ratio of dissociated acid and conjugated base over the concentration of associated chemical. Okay, in simple words, this whole sentence actually means that when an acid, suppose we took a weak acid, it gets dissociated or it gets ionized in the aqueous solution in the form of the conjugated base and in the form of a proton, right? So when we calculate the Ka value, that is the dissociation constant of this particular acid, it would be equal to the ratio of the concentration of the conjugated base multiplied the concentration of the H plus ion released divided by the acid that we have taken. This much have you understood? Like this would be the mathematical definition of the dissociation constant, right? And pKa would be the negative logarithm of this Ka, this dissociation constant. How to convert this? How to convert the K into the pK? That's what I'm telling. No, this if the pK is given in a question, or we have calculated the Ka value. This is the Ka value. Sorry, this is the Ka value, and this Ka value. Wait a second. So this is the Ka value. Ka value whenever pK value, whenever the Ka value is given in the question, right? And or we know the Ka value we have calculated through this formula, then what we can do is to calculate pKa from Ka, we can take the negative logarithm of Ka value. This is how we calculate the pKa value from Ka. Did you understood? Yes, the pK is a point where it's deprotonated. Yes. pK is the value where the particular group is deprotonated. So we'll be coming into the definitions. You'll be understanding it when I'll be reading the other particular concepts. So another important characteristic of Pi is that Pi is the characteristic of an amino acid or the polypeptide chain. So the Pi is basically, it tells the whole characteristic of the whole amino acid. We are talking about the entire amino acid consisting of all the groups, the COH group and the amino group and the R group that would be involved for a particular amino acid. So it would be telling the whole charge, what would be the particular charge on the amino acid when we take reference of all these groups. So it tells the entire charge present on the amino acid, while pK is basically the characteristic of a particular functional group. So for carboxyl group, the pK value would be different. For the amino group, the pK value would be different. And for R group, the pK value would be different. So pK value basically tells that the value for a particular group in the amino acid. It doesn't tell us about the whole amino acid, right? And on that basis, what would be the charge on amino acid that we can calculate? Understood? Yes, coming to the third definition. Now, how do we calculate Pi? So to calculate Pi, we take the average of the flanking pK values. What do you understand by this? So Pi is basically the average of the average of the near pK values. It could be like for pK1, we generally consider pK1 as the pK value for carboxyl group, and the pK2 value we generally consider the pK value for amino group, right? So taking the average of these two values, we can calculate what would be the pi value. This is for the general amino acids such as glycine, valine, all these 13 amino acids which have only two groups that get ionized into the aqueous solution. That is the COH group and the amino group. For them, we basically calculate the pi through this formula. But for certain different categories of amino acids, such as the basic amino acid or the acidic amino acid, for them we use the pK values that are near pK values, and we take the average of those pK values. It could be the pK 2 plus pKr divided by 2, or it could be the pK 1 plus pKr divided by 2. Depends on about which amino acid we are talking about, right? Now coming to the rules that for a particular amino acid that we apply according to pi and pK, right? So when we say that we consider a particular pH and it is equal to the pi of the amino acid, right? Then what happens? The amino acid generally exists in its Zwitter ionic form. What would be the Zwitter ionic form? It would be, there will be R group. This is the general structure of amino acid, right? So this would be the Zwitter ionic form, like minus and the plus charge, like it would be in its diprotic form. Both the charges would be present in it. The charge would be neutral, and electrophoretically also speaking, the mobility of the amino acid will also be 0. So at the first rule for the pi is that when the pH is equal to pi, the amino acid would be present in its Zwitter ionic form. There would be no net charge on the amino acid, right? Then coming to the rule for pK. Now for pK, it's written that when pH is equal to pK, then what happens? It is particularly for a functional group. Either it could be for carboxyl group or it could be for amino group, right? Now here it says that both protonated and deprotonated form group exists in equal concentration. So when the pH would be equal to pKa, both protonated and deprotonated form of the carboxyl group, if we consider about the carboxyl group, or if we specifically take the amino group, both of these concentrations would be present in equal amount. How? So here is the general structure. If I say for carboxyl group right now I'm considering, right? So this is the deprotonated form for carboxyl group. So at pH, when pH is equal to pK, this concentration of amino acid would be equal to the concentration of COO minus, where carboxyl group is basically present in its deprotonated form. So both of these concentrations would be present in equal amount at pH, when pH is equal to pKa. Understood? There was one question on NET exam, okay, where pi was to be found and given was pK1 and pK2, right? For alpha carboxyl group and amino group, and pK2 beta NH3. Okay, there was a beta NH3 group present in there. So how will you calculate the pi? So for this, what happens is pi would be basically the average of two nearest pK values. If the pK values, like if here it is given that pK1 or pK2, if pK1 and pK2 are very much like nearby to each other, the values are very much nearby to each other, then the average of these two values would be taken. And if the pK2, that is for the beta NH3 group, if that is very much near to pK1 or pK2, then both of those values, the average of both of those values would be taken. So whosoever pK is very much near, the values are very much near to each other, those values, the average of those values need to be taken to find the pi. Am I able to give your answer? Did you understood? Ankita, it was your question, right? Did you understood that? Okay. So Mahima says that for basic amino acids like histidine, lysine, arginine with positive side chains, isoelectric point is average of the Ka, pKa of the two basic values. Yeah, yes, correct. Mahima, you're correct. So coming to the next explanation, the next rule it is given for Pi is that when the pH is greater than Pi, when the pH in which a particular amino acid is present, it is greater than Pi, then what happens? The net charge on the amino acid, the complete amino acid is positive. Okay, so electrophoretically speaking, when the pH is less than Pi, the net charge on the amino acid is positive. At that particular time, electrophoretically, if we speak in a gel, how the amino acid mobility will take place. Now, here is the anode plus, and here is cathode. Right? So, when pH is less than Pi, the amino acid, the charge on amino acid is positive. So, amino acid would be moving from anode to cathode. This would be the movement. Right? And opposite happens for when pH is greater than Pi. When pH is greater than Pi, the net charge on an amino acid is negative. Right? Here it was positive and here it would be negative. So electrophoretically, if we speak, how would be the mobility of the amino acid? So here is the anode, here is the cathode. So amino acid would be moving from this cathode towards, So amino acid would be moving from cathode to anode. This would be the mobility, the direction of the mobility of the amino acids, right? Coming to the pKa. Could you explain, okay. Noor Jahan, could you explain the pH equals to pKa concept once again? Yes, of course. So at last, I'll be considering this question of yours. Right now, let me proceed further, right? Now coming to the next rule of pKa. Next rule of pKa is that when the pH is equal to pKa that we have discussed, right? When the pH is equal to pKa, what happens that both the protonated and deprotonated form of the group exists in equal concentration. That's what I explained. Like the amino acid would be present in its deprotonated and protonated form. So general structure of amino acid, this is the deprotonated form of amino acid, right? This is the deprotonated form of amino acid where carboxyl group, if we consider, this has not yet lost its H plus ion, right? So it is present in its deprotonated form. At pH equals to pKa, this concentration would be equal to the concentration where amino acid is present in its deprotonated form if we consider about carboxyl group. So this is the NH3 group, right? This is the CH, this is R and COO minus. So this would be the structure of amino acid. Now both of these concentration would be present in equal amount. The concentration would be equal in the aqueous solution. So at pH equals to pKa, both of these concentration would be present in equal amount, right? The deprotonated form and the protonated form of the carboxyl group. Here we are specifically speaking about the carboxyl group, not the amino group. So both of these concentrations would be present in equal amount. Then coming to the next rule for pH, for pKa. So when the pH is less than pKa, then what happens? Then the group majorly exists in its protonated form. So suppose we consider pH equals to 1, right? At pH equals to 1, what happens? The amino acid is basically present in its deprotonated form. The carboxyl group has not yet lost its H plus ion, and the amino group is also present intact. As we know, for generally speaking for amino acid, the pKa value for carboxyl group is usually 2 that we consider, right? So this value 2 is greater than the pH value. So at pH 1, which is highly acidic pH, the amino acid is present in its deprotonated form, right? The carboxyl group is present in its deprotonated form. That's what it has said here. And what happens? And what happens when the pH is very much greater than the pKa value? Means it is a basic solution that we are talking about, right? So let us suppose that we take the pH equals to 7, right? Then what happens for the general amino acid? The carboxyl group would be present in its deprotonated form, right? It would be present in its deprotonated form. Because as we know that the pKa for the carboxyl group usually for amino acids is 2. And 7 is very much greater than the value 2. So what happens? The carboxyl group, it loses its proton and gets deprotonated. Understood this much? Yeah. Then coming to the last thing that we consider both for pKa and pi. So for pi, it is being said that near pi value, there is no movement in electrophoretic gel. That I have already told that at pi value, when the pH is equal to pi, then what happens? Two major things we need to consider, that the net charge on the amino acid would be neutral, that would be 0, and the mobility of amino acid electrophoretically, it would also be 0, right? Coming to pKa, so near pKa value, a group can act as buffer. So when the pH is equal to pKa, when the concentration of the amino acids, like both in its protonated and deprotonated form for a particular group is in equal amount, at this particular time, what happens? The solution consisting of that amino acid, it basically behaves like a buffer. So even if we add little bit amount of like OH minus ion or acid, anything, OH minus ion. So anything we add or acid if we add into it, there would be no change in the pH of the solution. At that time, this solution basically acts as a buffer. So at pH equals to pKa, it is being said that the group basically acts as a buffer, right? Then coming to the next slide. So here, what it is being said, it is basically telling about the acidic and basic properties of amino acids. So from the structure itself, how can we decide like when the amino acid would be behaving as an acid or when it will be behaving as a basic solution on the basis of the charge on these particular groups, side groups that is being there. So this figure also says the same thing which I have explained through the concept table. Okay, so there is not much to explain here. Coming to the next slide. So this slide basically gives us this. There is a table, it is being mentioned here, where we have taken different pi and the pKa values of amino acids. These values, you need to remember it. So pi values you cannot understand until and unless you are thorough with the structure of amino acids. And I hope that all of you are knowing the structure of each and every amino acid. Because for understanding pi, you need to understand what is the structure of each and every amino acid, what is the single letter symbol for every amino acid, right? So here, if we say, so for glycine, it is given. So there would be like 13 amino acids that will just have 2 pK values. 2 pK values, pK1 for carboxyl group and pK2 for amino group, right? So for these, the R group that is being present in these 13 amino acids, it is non-ionizable. So what are these 13 amino acids? So first is the glycine, second is the alanine, proline, valine, leucine, isoleucine, methionine, phenylalanine, tyrosine, serine, threonine, cysteine, asparagine, and glutamine. These are the amino acids for which there are only 2 pK values present, right? Now, for each and every amino acid, you need to remember what is the symbol for, like single letter symbol. And you also need to remember which all amino acids they are being considered into the non-polar aliphatic R group, and which are the amino acids in which there is an aromatic R group present and they are non-polar. For polar charged amino acid R group, there are like serine is there, threonine is there, cysteine is there, asparagine is there, and glutamine is there. For cysteine, which has a thiol group, if we talk about cysteine has the R group as a thiol group. Right? And for its, the pKr value is 8.18. This is also something which you need to remember. Then come the special category of amino acids, the positively charged R group containing amino acids and the negative charged R group containing amino acids. So positively charged and positively charged, there are like 3 amino acids, lysine, arginine, and histidine. So for these 3 amino acids, there will be 3 pK values, right? If we consider about the acidic and basic amino acid, for both of these we consider, right? So for these amino acids, there will be 3 pK values. One would be the pK1 for carboxyl group, second would be the pK2 for amino group, and third would be the pKr group, right? So for lysine, it's given that the pKr value is 10.53. For histidine, it's 6, which is near to the physiological pH of our body, that is 7, right? And for arginine, it's given that the pKr value is equal to 12.48. So here what we need to understand here is that for arginine, it's the pK value, that is the pK value for the R group. It is very, very high. Like, it is very basic. So it is very much difficult to like deprotonate this particular group. Like, removing the H plus group from this R group of arginine would be very difficult, right? So let me ask you a question. What would be the R group for arginine? Like, what common name, with what common name we call it? For arginine, I'm talking about. Okay. Sovri Mitra, she says that, does that mean that for all these 13 amino acids will have the same PI? Yeah, it would be similar. Because pK1 and pK2 values are same for all these 13 amino acids. So the PI, when we calculate the average of these pK values, it would become same. Except for proline, like the proline is the only amino acid for which what happens that the pK2 value is something different, pK2 and pK1 value. For proline, the pK1 value is 1.99. It's not equal to 2. And for proline, the pK2 value is equal to 10. Right? For proline is the only amino acid for which the PI value won't be similar. Am I able to give you answer? Yeah, guanidino group. Yes, you are correct. So Swapnil and Vishal gave the right answer. R is the name of the arginine. R is the name of arginine. Arginine is the amino acid, Mahima. I'm talking about what would be the R group for arginine. Like, what would be the common name? Okay, it would be guanidino group. Similarly, it goes for the acidic amino acids, having the negatively charged R group, that in which basically aspartate and glutamate comes. So here we will be having the 3 pK values. One would be the pK1, another would be the pK2 value, and last would be the pKr. That will differ for both aspartate and glutamate, right? So pK1 would be 2, like it is nearby or equal to 2, and the pK2 value would be 9, that we usually consider for all amino acids. And for pKr, for glutamate, that is being the single letter word for glutamate is E. So for it, the pK value would be 4.2. And for coming to aspartate, D, that is the single letter symbol for aspartate. This is also something which you need to remember. So here the pK value for the aspartate, it would be 3.62. So these are highly acidic groups, the R group that are present in these amino acids, right? So this table is very much important. Go through this table. It is also being given in your standard book, that is Leringer. From there only I've taken this table. You go through that book and this table, because here there are very much important things that you need to memorize. Then coming to the charge on amino acids at different pH values. Okay. So charge on amino acids, how do we, the charges on amino acids are different when we consider different pH values. So firstly, if we take the pH as 1, it is a highly acidic pH, right? The solution is highly acidic here. So at that pH, what happens? The net charge on the amino acid is positive. How? This is the general, wait a second, let me change the color. So this is the general structure of the amino acid. Now here what happens is at pH 1, that is the highly acidic solution, the net charge on the amino acid is positive due to the amino group, because the carboxyl group has yet not deprotonated, right? After that, slowly when we increase the pH, when we like add OH minus ion into the solution and the pH gets increased, then what happens? The deprotonation occurs. Deprotonation of the carboxyl group occurs. And what happens? The slowly the carboxyl group, it starts losing its H plus ion into the solution and it becomes negative. So at that point of time when the pH of the solution, it becomes equal to the PI value, or it reaches to like physiological pH. If we say here it is given the physiological pH, that is pH we have taken is 7. So at that point of time, what happens is the carboxyl group has lost its H plus ion entirely and had become completely deprotonated, and the H plus, the ammonia group, the ammonium group, it still consists of the proton and has not deprotonated. So at this point of time, the amino acid would be present in its deuterionic form, right? This is when the pH is equal to Pi. Also known as the isoelectric point, net charge is 0 and mobility is also 0 for the amino acid electrophoretically. Then coming, if we again increase the pH, so coming from pH 7 to pH 13, then what happens? Then this amino group also, it also starts losing its proton and gets deprotonated, right? It gets deprotonated and acquires this particular, So here what happens that amino group has lost all its hydrogen ion, and carboxyl group has also deprotonated. At this particular time, the amino acid is basically present in its N-ionic form, right? So it will only have the negative charge due to the carboxyl group, right? So this is how the charge on the amino acids, it like gets changed when we consider different pH values. So on the basis of the pH value, how the charge of the amino acids gets changed, this is being explained through this figure. Are you able to understand this? All groups are protonated. At what point of time you are saying, Vishal, that all groups would be protonated? Yeah, at like first stage, if you are saying that here all the groups would be protonated, like COH will also have its H plus intact, and NH, the ammonia also will have its H plus intact. Yeah, right. Now coming to the characteristic titration curve for amino acids, right? For general amino acids, we are considering here first. Now, titration is something which all of you would have done in your 12th. At that time, there was just color change that you used to see. Now, here is the graph that is being shown. So through this graph, how do you understand like how the characteristic of like properties of amino acid that we can like deduce from this particular titration curve, that we need to understand here. So here I have taken the example of glycine, right? So initially what happens is, when we consider let me change the color. So when we consider the pH very low, let us take it as 1. Okay. At very low pH, what happens is the amino acid glycine here we are taking, it is present in its deprotonated form, right? This is the first structure that is being shown here. It is present in its deprotonated form. The carboxyl group has not yet released its H plus ion, and NH3 is also present in its like protonated form. Now, what happens when slowly and steadily we start adding OH minus ion from outside into the aqueous solution, and the pH of the solution, it gets increased? Then what happens slowly and steadily, this carboxyl group, it starts losing its H plus ion, right? So initially at pH equals to 1, the net charge on the amino acid would be 1, plus 1, sorry. It would be plus 1, right? Plus 1 because of the amino group. Then slowly and steadily, if the pH of the amino acid or the solution gets increased, then what happens? The carboxyl group, it starts losing its H plus ion. And it comes to a point known as pK1. This is the pK1. Yeah, this is the pK1 value, where what happens when the pH is equal to the pK1 value, that is equal to 2 for generally speaking for amino acids, then what happens is 2.34 for glycine, here it is written, we'll consider that only. Here at this particular point of time, the 50% of the amino acids are present in its deprotonated form, and 50% of the amino acids are present in its protonated form. 50% would be present in this structure, and 50% would be present in this structure, right? This is for the first stage. I'm saying there are two stages here. This is the first stage, this is the second stage. Firstly, in first stage, we are considering about the carboxyl group, the protonation and deprotonation of the carboxyl group. In the second stage, we will be considering the protonation and deprotonation of the amino group, right? So till here, what happened is we started with pH 1. Net charge on amino acid was plus 1 because the carboxyl group has not yet deprotonated, and the whole of the amino acid is present in its protonated form, right? Slowly and steadily, when we increase the pH, then what happens? The carboxyl group, it starts losing its H plus ion. And at the point where pH gets equal to pK1, this is the midpoint here, it is being shown, which is equal to 2.34 for glycine. Then what happens is the net charge on amino acid, it would be 0. At this particular point of time, half of I'm not talking about this particular thing. Yeah. So we are talking about the pK1 value. This point of time, I'm saying that pK1 value, at this particular point of time, what happens? When pH is equal to pK1, half of the amino acid is present in its protonated form, and half of the amino acids is present in its deprotonated form. So both of these structures are present in 50-50% concentration. So this is the point of inflection where it is basically considered the buffer region. That is, even if we add OH minus ion into the aqueous solution, still the pH of the solution won't get changed, right? This is that particular pH when pH is equal to pK1. Are you able to understand what I'm saying? Do you want me to repeat it? Clear? Okay. Vishal, it's clear? For everyone, is it clear? Yes, Mahima, you are right that net charge on amino acid basically depends upon the surrounding pH, right? At midpoint, okay, acidic acid you are talking about, and yeah, are equal, and the pH is numerically equal to pKa, right? Yes, Mahima. Repeat it, okay. So one of the person, he says that I need to repeat it, okay, you didn't understand it. So how did we start it? So let me make it easy for you. We are considering here two stages, right? First one is this stage, second one is this stage. In first stage, we are considering the protonation and deprotonation of the carboxyl group, and in second stage, we'll be considering the protonation and deprotonation of the amino group, right? Now in first stage, initially when we started with pH equals to 1, which is very acidic pH, right? At that particular pH, what happens is the amino acid is present in its deprotonated form. Deprotonated form in the sense the carboxyl group has yet not released its H plus ion, right? So whole amino acid would be present in its deprotonated form. This is the structure in which the amino acid would be present. And the net charge on the amino acid at this particular point of time would be +1, right? After that, what happens is, slowly and steadily when we increase the pH by adding the OH minus ion into the aqueous solution, then what happens? The carboxyl group, it starts losing its H plus ion, and it will become, and it will be ionized, and it will form this particular form. It will be inside the aqueous solution, right? And when the pH is equal to pK1 for general amino acid, it is being considered nearly equal to 2. For glycine, it's given 2.34, right? So at that particular point, what happens is, I'm talking about this particular point, when pH is equal to pK1. Then 50% of the amino acids are present in its deprotonated form, and 50% of amino acids are present in its protonated form. So both of these structures are present in its 50% concentration into the aqueous solution. This much have you understood? And this pK1 value, where pH is equal to pKn, it is also an inflection point which is being considered as the buffer region. Buffer region in the sense, even if we add a little bit amount of acid or base into the solution, there would be no change in the pH of the solution, right? Then coming to the second stage. So second stage, if it'll come, so slowly and steadily, if we start increasing the pH after this pK1 value, then what happens? There is a sudden increase in the pH value of the solution. What happens in here is that the amino acid, it reaches to a point where the net charge on the amino acid, it is neutral, right? At this particular point of time, this is the midpoint I'm talking about, when the pH is equal to Pi. So at this particular point of time, the amino acid, the carboxyl group, has completely lost its H plus ion, right? And had completely deprotonated. And the second group, that is the amino group, the H plus ion, it has slowly it has started to lose its H plus ion. So at this particular point of time, the net charge on the amino acid is 0, right? This is the zwitterionic form. Now here I haven't given the value of the Pi for the glycine. Now you people would be calculating the Pi value for the glycine, and you would be knowing the formula. Then coming to the second stage. Second stage, after crossing the Pi value, what happens? When we again increase the pH of the solution, let us consider the pH of the solution as 13. This is a highly basic solution. Then what happens is, then the amino group also, it has also started losing its H plus ion, right? At a midpoint of pK2, which is equal to 9.60 for glycine, at that point what happens is, the 50% of the amino acids are present in its deprotonated form, specifically speaking about the amino group. So this would be the deprotonated form, means it would be present in zwitterionic form, and 50% of amino acid would be present in, so pH equals to pK2 here we are taking, that pK2 is basically equals to 9.60, right? And 50% of amino acid would be present in its deprotonated form for amino group. So these two structures would be present in 50-50% or equimolar concentration. In equimolar concentration, these two structures would be present in a solution at pH equals to pK2. Now when we increase the pH from pK2 and we consider the pH equals to 13, then what happens is, at that particular point of time, what happens? The amino acid has completely, the amino group has completely lost its H plus ion and had completely become deprotonated. So at this particular point of time, the net charge on amino acid would be -1, right? Now I want you to answer me what would be the pi of the glycine. It would be basically the average of these two pK values, since it is occurring in the middle, right? It would be, yeah. Vishal says it would be 5. Yeah, approximately it would be 5. 5.97. Yes. So pi value would be approximately 5.97. How did we calculated it? We took the average of pK1 plus pK2 divided by 2. So by this formula, you will be able to calculate the pi value for glycine, right? Then coming to the titration curve for glutamate and aspartate. So glutamate and aspartate, they basically belong to the acidic group of amino acid, right? They have an R group which consists of an extra carboxyl group in them. So considering for glutamate, what happens is, initially when the pH, let us consider pH equals to 1. So here what happens is, yes, initially at pH equals to 1, what happens is, the glutamate, the structure of glutamate, I'm hoping that everyone knows. Here also it's given, the structure of glutamate is being given here. Right? So from here you can take the reference. Now what is happening, initially when the pH is equal to 1, that is the solution is highly acidic, there is no, like the whole amino acid would be present in its protonated form. There will be no like deprotonation of carboxyl group which will be taking place. So at this particular point of time, the net charge on the glutamate would be +1 because of the amino group, right? Because of the amino group, the charge on the amino acid glutamate would be +1. Then as we increase the pH and we reach at a point known as the pK1, then what happens is, at this particular point of time, 50% of amino acids would be, glutamate would be present in its deprotonated form, and 50% would be present in its protonated form. Protonated form we are considering in the with respect to the carboxyl group here, right? The alpha carboxyl group. We're not considering the gamma one. So alpha carboxyl group gets deprotonated here. Then as we increase the pH, what happens is, we reach to a point where pH is equal to pi, right? At this particular point of time, what happens is, the alpha carboxyl group has completely deprotonated, has lost its H plus ion, and the gamma carboxyl group, it has started losing its H plus ion. So this is the point where pH is equal to pi. This is the point where net charge on the amino acid would be equal to 0. So the amino acid would be present in zwitterionic form, and net charge on the amino acid would be 0. Here also I haven't given you the value of pi. You would be calculating what would be the value of pi, right? Then coming to, as we increase the pH we are increasing more. After the crossing the pi value, when the amino acid, when it reaches to the pKr value, for glutamate, the pKr value is 4.25. At this particular point of time, the amino acid would be present, the 50% of amino acid would be present in its zwitterionic form, and 50% of amino acid would be present where the net charge on amino acid would be -1. So this is the structure here, which is what it is being given for glutamate, right? Then if we increase the pH after crossing the pKr value, then when we increase the pH, it reaches to a point known as the pK2 value, where the amino group, it has started releasing its H plus ion and gets deprotonated. So at this particular point of time, 50% of amino acid would be present in its deprotonated form for amino group, and 50% of amino acid would be present in its protonated form for amino group, right? So at pK2, that is 9.67. Then further, if we increase the pH, when the pH is equal to 13, let us consider, which is above 9, Then what happens is the amino group has completely lost its H plus ion. It has completely become deprotonated, and the net charge on the amino acid at that particular point of time would be -2 because of the gamma carboxyl group which having the negative charge and the alpha carboxyl group having the negative charge, right? And the amino group, it has completely lost its H plus ion. So are you clear with it, or you want me to repeat it? Right. Yes. So yeah. So what would be the pi value for this particular glutamate? What would the pi value, and how did you calculated it? Yes, so Mahima says it would be 3.22. Vishal says it would be 3.22. Yes. So, yeah. So, how we'll be calculating this? So, the pi value would be equal to. So, here we can see that the pK1, that is 2.19, and the pKr value, that is 4.25. These are the near pKa values for the amino acid glutamate. So these two values, the average of these two values would be considered. So the pK1 plus pKr divided by 2, that is 2.19 plus 4.25 divided by 2, and we will get the value of pi, which is equal to 3.22 for glutamate, right? Am I clear? Average value of the two pK where amino acid is 0. Yes. Pi is that value where the net charge on amino acid is basically 0. Right? So moving from glutamate, coming to the basic amino acid, lysine and arginine. So for lysine and arginine, similarly as we considered for glycine and the aspartate and glutamate, there also the characteristic titration curve is different. Here also I haven't given the value of pi which you need to find, and at the end I'll be asking you. So pi it's a question mark for all of you. Now the general structure for lysine, what happens is the R group in lysine is basically an epsilon amino group, right? This is the R group. And may I know what would be the pKr value for lysine? Yes, in the table it is being given, like I have explained it already. Most of you would be knowing. I would be expecting answer. What would be the pKr value for lysine? Like for what would the pKr value for epsilon NH3 group? No, I'm asking, yeah, Garima, I'm asking what would be the pKr value? What would be the value for the epsilon NH3 group? It would be, yes, Vishal, it's right. It would be 9.74. So the pKr value, 4.3154 for glutamine. No, I'm not considering about glutamine. Here I'm asking about lysine, and for lysine, what would be the pKr group? So the pKr for lysine is basically, if you don't know, it's about 10.53, right? Yes, Vishal, now it's correct. So pKr would be 10.53 for lysine. Now what happens is initially at pH equals to 1, when the solution is highly acidic, the whole amino acid is present in its deprotonated form, right? So the total charge on amino acid, it would be +2 because of the epsilon amino group and the alpha amino group, right? Because of these two groups, the total charge on the lysine would be +2. This would be at pH equals to 1. Now, as we increase the pH and we get to a point where pH is equal to pK1, then what happens is, at this particular point of time, where pH is equal to pK1, the value of pK1 is 2.18, the carboxyl group, the alpha carboxyl group, it has slowly deprotonated itself, right? So 50% of the carboxyl group gets deprotonated and is present in its anionic form, and 50% of the carboxyl group is deprotonated and is present in its COH form, right? This is what happens for carboxyl group at pK1 value. Now, as we increase the pH, there is a sudden increase in pH you can see, like when we add OH minus ion into the aqueous solution. And when the solution, it reaches to the pH of 8.95, that is pH equals to pK2. Then what happens is, the alpha amino acid, it has started losing its proton and gets deprotonated. So this is the value, that is the 8.95, where pH is equal to pK2 value, right? At this particular point of time, what happens is, this alpha amino group, it has started losing its proton and gets deprotonated, and 50% of this glutamate is present in its protonated form, where amino group is present in its NH2 form, and 50% of glutamate is present in its deprotonated form, where amino group is present in its NH3 plus form. Okay? Then what happens is, after crossing this pK2 value, when we come to a value where pH is equal to pi. Now, what is the pi value that you need to find out? Okay. At this particular point of time, what happens is, the alpha amino group has completely lost its H plus ion and has become deprotonated, and the carboxyl group has also completely lost its proton and become deprotonated. So at this particular point of time, what happens is, the net charge on the amino acids is 0. So this is being considered as the pi point for lysine, that is the isoelectric point. And right after that, when we increase the pH and we cross the pi value and we reach to a point where pH is equal to pKr. pKr is basically the pK value for the epsilon NH3 plus group, right? At this particular point of time, what happens is, the amino group, the epsilon amino group, it has started losing its proton. So 50% of amino acid would be present in which the epsilon amino group has deprotonated, and 50% of amino acid would be present where epsilon amino acid has not yet been deprotonated and it is present in its cationic form, right? This is the cationic form. Here it is lost and it is deprotonated. So at this particular point of time, equimolar concentration of these two forms would be present for glutamine, right? For the epsilon amino group. Then as we cross this particular pKr value and the pH is increased and it gets equal to 13, then what happens is, the epsilon amino group has also lost its proton and gets deprotonated. The amino group has also, the alpha amino group has also deprotonated. The carboxyl group has also deprotonated. And at this particular point of time, the net charge on the amino acid is -1 because of the alpha carboxyl group, right? Did you understand this? So Swapnil says, for acidic amino acid, take average of pK of COH group and the pKr, and the basic amino acid, take the average of pK of NH2, and yeah. So basically, for if we want to, generally, if I would say for both, we don't know if, like, consider that the amino acid, about the amino acid, we don't know that it is acidic or basic, and we have just given the pK1 value, pK2 value, and pKr value, right? So whichever values would be near, like the values would be similar, or whichever values would be very much near to each other, the average of these two values would only be taken. Now for basic amino acid, what happens, such as lysine, the two pK values which are nearby to each other is pK2 value and pKr value. pK2 is 8.95 and pKr is 10.53, right? So we'll be taking the average of these two pK values and we'll be calculating the pi. For acidic amino acid, what happened was, the two nearby the pK values were pK1 and pKr. So we were calculating the pi on the basis of how we calculated, by taking the average of pK1 and pKr. So this is how we do. in question paper, it may happen that you are not being given whether the amino acid is acidic or basic. Then what will you do? You will consider whichever the pK values that are being given are very much near to each other. The values are very much near to each other. You will take the average value of those two pK values. Okay. Now have you understood? Why are similar in two group, ma'am? I didn't understood you, Kirtana. What are you asking? Please repeat your question. Red color is not clearly visible. Okay, I'll change the color. Sorry. So coming to the titration curve for histidine, if we talk about. Now, histidine is an amino acid. For, if I say the pKr value for histidine is 6, right? Which is very much close to the physiological pH of our body, that is 7, right? Now, histidine also lies into the basic amino acid category only with lysine and arginine, but the characteristic titration curve for histidine is different. Let us see how. Now, for histidine, as we know that the R group, the name of the R group is basically the imidazole ring is present here. Right? So initially what happens when the pH is equal to 1, right? Here let us consider pH is equal to 1. So the structure of amino acid is being given here. So at this particular pH, the net charge on the histidine is +2. How? 1 is coming from the NH3 plus group, that is the alpha amino group, and second is the imidazole ring. Here the amino group which is being present, because of these two groups, the net charge on the amino acid is +2. And at this particular point of time where pH is equal to 1, highly acidic solution, the carboxyl group has yet not deprotonated, right? Then when we increase the pH, then what happens is it reaches to a point known as the pK1 value. This is the pK1 value. Right, this is the pK1 value for histidine, which is equal to 1.82, or you can consider it as nearby 2, if you would say, right? Then what happens is that the 50% of that equimolar concentration of amino acids are present in its protonated and deprotonated form with respect to the carboxyl group, right? So 50% of the histidine would be present in its deprotonated form for the carboxyl group, and 50% would be present in its protonated form for carboxyl group, right? Then when we further move, and this is also known as the buffering point, when we further move and increase the pH and we reach to a point where pH is equal to pKr. So at pK1 value, the net charge on the amino acid, it would be +1. How it would be +1? Because the carboxyl group, it has started losing its proton, it has come to its anionic form, and the amino group is present in its plus form. So both of these, like, it will cancel each other's effect, and the net charge would be basically due to the imidazole ring, okay, amino group present in the imidazole ring. So at pK1, the net charge on the amino acid would be +1. Now when we further move and the pH is equal to pKr, then what happens is, so pKr for histidine is 6, as I have discussed earlier. So the imidazole ring, what happens, the amino group in the imidazole ring, it starts losing its proton, right? Then the net charge on the amino acid, it would be 0. Because of, since the carboxyl group has already deprotonated, alpha amino group has yet not deprotonated, and the amino group of the imidazole ring, it has deprotonated. So due to this reason, the net charge on the amino acid would be 0. So this would be the point at which the pH is equal to the Pi, right? And it would be present in zwitterionic form. Now, mind you, this particular point would be present in between the pKr value and the pK2 value, right? So pKi, I want you to find out the Pi value for this amino acid. Now here also, like similarly as we have considered for other amino acids, the two pK values which are near to each other, like the values are very much close to each other, we'll be considering the average value of those two pK values, and we'll be calculating pi. So what would be the pi for histidine? Pi value for histidine. Yes, I'm waiting for the answer. Mahima wrote it would be 7.59. Yes. So the pi value for histidine would be 7.59. How did we calculate it? Pi would be equal to the pKr value plus the pK2 value. These are the near pK values for histidine, and we'll be taking average of these two values, and then we'll be able to find that the pi value for the histidine is 7.59, right? So here we'll write 7.59. So here is a question answer session. Now you have to answer these questions. So it would be homework for both of you, like for all of you. So you need to find out, for the first question it is being written here, that an amino acid contains no ionizable group in its side chain. It is titrated from pH 0 to 14. Which of the following ionizable state is not observed during the entire titration in the pH range of 0 to 7? So which of the structure won't be present in the solution, that you need to find out. Okay, which option would be correct? We'll be discussing this in the next session tomorrow at this very time, like from 11 a.m. it will be starting. And this also you have to find out what would be the net charge on this particular peptide. Okay. For this, you need to remember the single letter that we use for the particular amino acid, right? So at pH 1, what would be the value of the peptide, and at pH 13, what would be the value of the peptide, and what would be the value of the peptide at pH 7? This you need to find out, and this would be your homework, and I'll be discussing both of these questions tomorrow, right? So it is being late now, so I'll be ending up the session. Hope you enjoyed the session, right? Some people have already started giving the answer. Right, okay. We'll be discussing this question tomorrow, okay? So before going, I would like to say that you can fill the feedback form that is being given in the link in the description. And after filling that feedback form only, you can download the free sample papers, okay? Thank you very much.